Hi everyone, and welcome to What's Up Physics. I'm Aishwarya, and today we're going to go over Newton's third law and a bunch of problems related to those concepts. Let's get into it. Definition of Newton's third law. So you may have heard this definition before. Newton's third law states that for every action, there is an equal and opposite reaction. In other words, the third law describes the paired forces that two objects exert on one another during an interaction. Let's go over a scenario. Say box A is pushed and it collides into box B. Box A would exert an applied force on box B, right? Now, what Newton's third law says is that there should be an equal and opposite reaction for the action of box A colliding with box B. What this means is that box B would also exert a force back on box A, like this. This force would be equal in magnitude to box A's force on B, but opposite in direction because it would be exerted back onto box A. Alright, so I'm going to take this knowledge and summarize it once again for you guys. Fact 1. Both boxes exert a force on each other. It doesn't matter that only box A was moving and it was the one that hit box B. Box B still exerts a force back onto box A. No matter what the interaction looks like, if one object exerts a force on something, the other must exert a force back. Fact 2. The magnitudes of the forces the boxes exert on each other are equal. Newton's law states that each reaction has an equal and opposite reaction. And side note, this is true regardless of the masses and the accelerations of the objects before their interactions. Our objects could literally be a fly and a school bus for all we care. Even though the fly's mass is insignificant compared to the school bus, if the two collide, the forces on each other are equal. The force of the bus on the fly is not greater than the force of the fly on the bus. And this might be a little hard to wrap your head around, but we'll go over an example more in depth with this exact situation a little later in the video. And fact 3, the directions of the forces are opposite. This is a given if you think about it. If two objects collide, they're going to collide from different sides, so the forces that each object applies on the other is obviously going to be in the opposite direction. Third law, force pairs. So these are what we call the pair of equal in magnitude but opposite direction forces between two objects that are interacting. So force pairs are always going to be the same type of force. This is super duper key. Whether this force is normal force, gravity, applied force, friction, etc., the forces between two objects that are interacting, the force pair is always going to be the same type of forces. And this might cause confusion, so let's go over a few examples. I'm going to give you guys a force, and I want you to think of the corresponding third law force. Okay, number 1. A person pushes on a box. What might be the force pair for this? Okay, so for this, the third law force pair would be the box pushing back on the person. Again, this is because every action has an equal and opposite reaction. So the push on a box results in a push back on a person. And to better visualize this, think about this. Say you're trying to push your fridge. When you apply force on it, you yourself might start moving or sliding back. Why? Because as you push the fridge pushes back on you with equal force, causing you to accelerate backwards. The only reason you move backwards easily with that force while the fridge doesn't is because the fridge is much heavier than you. So it requires a much greater amount of force to cross that maximum static friction, which as we know is influenced by the normal force. Okay, so number 2. The ground pushes up on a person when the person's standing up on it, which aka this is a normal force of the ground up on the person. Okay, so the third law force pair for this would be the normal force from the student pushing back on the ground. If I can draw something like this. Okay, so don't get confused. The force pair for normal force of the ground on the person is not the gravity force on the person. It's not this. Why? Because for one, they're different types of forces. Third law force pairs must be the same type of force, so here that would be normal force. And for another, third law force pairs must act on different objects, and the normal force and gravity both act on the same person here. And also, excuse my arrows, because they look a little wonky, but just pretend that they're the same magnitude of each other. Okay, number 3. The earth pulls on the person with gravitational force. The force pair for this would be the person pulling back on the earth with equal gravitational force, like this. It might be weird to think that you're pulling on the earth with your own Fg, but this is true. There is a force of attraction between any objects that have mass, whether those be you, the earth, your pencil, etc. However, your gravitational force has no effect on the Earth because it has such a large mass. And we'll go more in depth on this later. Okay, and number 4. As the block is sliding on the floor applies a friction force on the block, like this. Okay, so the force pair for this would be the box rubbing against the floor with an equal amount of friction, like so. In a TV serial you're watching, 2 characters get into a fight and one punches the other. Describe the third law force pair in the interaction between these 2 people. Okay, so I'm just going to make a quick drawing first. So here we have our heroine, who is pretty badass. Okay, and she is going to punch. There's her fist. Oh, she has 5 fingers. Yeah, okay. She's going to punch the face of this annoying guy over here. Okay, perfect. So we know that our heroine over here exerts a force with her fist on this guy's face. So that's one of the forces in our force pair. It's the force of this heroine's fist on our guy's face. So what might be the corresponding third law force? So it would be the force of this guy's face back on our heroine's fist, like this. Equal in magnitude to the force of the punch on the guy. Think about this. This is why your knuckles would hurt so much if you punched something. Whatever you punch will push back on your knuckles with the same amount of force you hit it with, which will obviously hurt. So, yeah. Effects of third law. Okay, so we've kind of already discussed this with the idea of you pushing the fridge. But although the forces of 2 objects on each other are always going to be equal in magnitude, the 2 objects might accelerate backwards at different rates based on their masses. We can rearrange Newton's second law, F equals ma, to see this. This can become A is equal to F divided by m. If the mass is bigger, the acceleration is smaller, and vice versa. So for example, let's say Doof and Perry are on skateboards over here. Doof is going to be 70 kg and Perry is 30 kg. So let's say Perry pushes Doof as hard as he can. Compare their respective accelerations afterwards. Which one is faster? Okay, so first let's draw the forces on Perry and Doofenshmirtz. We have the force of Perry on Doof, and then we have the force of Doof on Perry. And third law tells us that these 2 forces are equal. Which one accelerates back faster? Well, this should be pretty simple. Since both are experiencing the same force, but Perry has the least mass, he should be the one accelerating back faster. Okay, and here's that bus and fly example I wanted to talk about earlier, except it's a bee now. So if the bee and the school bus collide into each other, the force on the bus and the force on the bee are going to be equal in magnitude. And you might be wondering, wait a sec, but when the bus hits the bee, it might get squashed, but when the bee hits the bus, nothing really happens to the bus's motion. Yes, and that's again because they have different masses. We know that A is equal to F divided by m. Since the bus's mass is ridiculously huge compared to the bee, its acceleration is going to be next to nothing when the bee hits it. And plus the force of the bee on the bus is pretty small from the bus's perspective. So that combined with the fact that the mass of the bus is huge results in a really, really, really low, almost non-existent acceleration. But for the bee, the same magnitude of force that was insignificant on the bus has a huge effect on the bee. And that, combined with the fact that the bee has a really, really small mass, means that when the force squashes the bee, which that force is enough to squash a little bee, it might accelerate a huge amount in the opposite direction that it was going. Example number 2. This toy truck is attached to a spring. A string ties the spring tightly to a weight, compressing it. When the string is cut, the truck moves forward. Using third law, explain how this works. How could you modify the setup to make the truck move forward faster? Okay, so let's start by drawing out the forces when the string is cut so we can better understand the motion of the truck. When the string is cut, the compressed spring is released and quite literally springs open, as we can see in the photos over here. So in the process, it applies a force on the weight. Let's draw this and call it FSP, or Fspring, on weight. And I'm drawing this on the left image over here because there's just not enough space on the right one. Okay, so now according to third law, if the spring applies a force on the weight must apply an equal and opposite force back on the spring. So I'm going to draw this in red and call it F weight on spring. Now, recall that the spring is attached to the truck. So, the force of the weight on the spring is what causes the truck to move forwards, which forwards meaning to the left in this case. Okay, so now how could we make the truck move faster? Or in other words, how could we make it have a greater acceleration? So, let's apply our second law, F equals ma. For the acceleration of the truck to be faster, the force applied on the truck needs to be bigger. What is the force applying on the truck? It's the F weight on SP. But what caused F weight on SP in the first place? It was due to the force of the spring on the weight. F weight on SP was just a reactionary force to this first force over here. So we need to increase the spring force. Now recall that F spring is equal to negative kx, where k measures the spring constant or how tough the spring is, and x is a distance that the spring is expanded or compressed. In our case over here, we're talking about compression. Basically, to increase the force of the spring on the weight, we can either A, increase the displacement x of the spring from its natural state by compressing it more, or B, use the spring with a greater spring constant. Example number 3. Trying to get the same truck to move using a different method, Mariah attaches a sail at one end of the truck and a fan at the other end, as pictured below. When she turns on the fan, the truck doesn't move. Why is this? Explain using third law. Okay, so before we begin, I'm going to quickly go over how a regular fan cart works. So we have a cart on wheels, like so, and then we have a fan at the end over here. Now, when the fan is turned on, the system moves in the opposite direction that the fan is pointing in. This is due to Newton's third law. When the fan is turned on, it pushes on the air like this. The air then pushes back on the fan. Since the fan is attached to the cart, the whole system moves backwards with that push. Okay, so now that we've understood this, we're trying to prove why the setup with the sail does not move. We know, again, that the fan pushes on the air, like so. Sorry, it's a little bit hard to see. And then the air pushes back on the fan. But we actually have a second force pair over here. The air that the fan pushes goes and pushes on the sail with the force of equal magnitude. Then the sail provides a reactionary force pushing back on the air. Now, if we take a moment back and just look at the forces that are being applied to our system or to our truck, we can see why this truck does not move. The air over here pushes the fan to the right. The air over here pushes the sail to the left. Remember, the sail and the fan are both attached to the truck, and so we can treat all these parts as one system with the same acceleration. So we can see then that the air pushing the fan and the air pushing the sail exert two forces equal in magnitude but opposite in direction upon our system. Thus, the truck has no net force on it and stays in place when the fan is turned on because all the forces are balanced. Contact forces. So we've defined contact forces before. They're quite literally the force on an object due to contact, such as a tangible push or pull. Although there are specific types of contact forces, such as applied force, tension force, normal, etc., we also use the term or idea of contact forces to describe the third law force pairs between two objects in contact. So let's say we have these two boxes over here, and an external outside force pushes this pink box. The pink box would start pushing the green box, and the green box would push back with an equal force on the pink box. These forces, F pink on green and F green on pink, are the contact forces between the boxes. Remember that if our system includes both objects, then the contact forces are internal to the system. Though they might affect each box's individual movement, they aren't responsible for the movement of the system as a whole. In this case, the forces between the two boxes are internal to the system of both boxes. This force over here is the only external force to the system. Example number 4. Two boxes of mass 4 kg and 6 kg are at rest next to each other. A 10 Newton force is applied to the leftmost box, causing the system to accelerate to the right. Find the contact force between the boxes if the force is applied to the box of smaller mass. If that same 10 Newton force is applied to the box of larger mass, would the contact force between the boxes be greater, less than, or the same as before? Explain. Okay, so before we approach this problem, we're going to talk about it conceptually first. Think about this for a minute. Would the contact force between the two boxes ever be equal to the external force applied to the system, which in this case is 10 newtons? Now, it might be tempting to say yes, but the correct answer is no. Think about it this way. the 10 Newton force is applied to the system as a whole. Out of those 10 newtons, some of them are applied to accelerate the pink box. The rest of that force is applied to the green box via the contact force the pink exerts on the green. If that contact force itself was to be 10 newtons, then where would the force be to accelerate the pink box? There wouldn't be any left out of the net external force. So basically, how the setup works is that the pink box receives the entire 10 Newton push, and the reason it doesn't move like it has the acceleration of those 10 newtons is because the green box is applying an opposing force to the pink box. This opposing force is the contact force, and it reduces the net force on the pink box. In turn, the pink box also applies the same magnitude of force to the green box, a force pair, thus pushing it forward. Another way you could think about this conceptually is the idea that the net external force applied on the system is split between the two boxes. Some of it goes to accelerating the pink box and the rest to the green box. The amount that goes to each box depends on the box's masses. The more the mass, the greater the amount of force it needs to accelerate. But be careful, this isn't physically true. In our case, the net external force of 10 newtons is all being applied to the pink box, and some of that is being put to use to push the green box. But if the split force idea makes sense in your head, you could think of the concept like that. Okay, let's put numbers to this problem now. So in the first scenario, a force of 10 newtons is applied to the 4 kg pink box. We want to find the contact forces between the two objects, which are the force of the pink on green, Fp on G, and Fg on P, or green on pink. Okay, so again to restate, these are going to be equal due to Newton's third law. So let's draw the FBDs of the two boxes separately, or as their own independent system. The pink box, which I'll draw over here, it has a smaller normal and gravity force than the other one, and it has the 10 Newton force pushing it, I'll write that as Fa, pushing it to the right. And then it has a contact force of green on pink, Fg on P, pushing it to the left. This contact force must be less than 10 newtons because we know that the whole system of the two boxes is accelerating to the right. Since the accelerations of the system's objects must match the acceleration of the system itself, the individual box is also going to be accelerating to the right, meaning the F net on it must point right. Okay, now for the green box's system, the normal force and gravity are going to be greater because it's bigger. And it only has one force acting on it in the horizontal dimension. That's going to be the force of pink on green, Fp on G, pushing it to the right. So as we can see, the F net on each individual box is different. However, the boxes have a common denominator. They accelerate at the same rate. We can use this common attribute and the box's masses to find the magnitude of the net force on each box. Since the net force on the green box over here is just equal to the contact force, which is what we're trying to find, that's how we're going to be able to find it. We just need to find what this net force here is. And we're going to be able to do that via the acceleration of the system. Okay, so we need to find the acceleration of the system as a whole. The F net of the system as a whole is this 10 newtons. Because remember, the contact forces are internal and then our vertical forces are balanced, so that's the only force on our system as a whole. So F net sys is equal to 10 newtons, and that's going to equal to the mass of the whole system, which we'd have to add the masses of the individual boxes, so 4 plus 6, times the acceleration of the whole system. So this gives us that A sys is equal to 10 divided by 10, or in other words, it's equal to 1 meter per second squared. Okay. So now remember, since the system's acceleration is going to equal the individual box's acceleration, the acceleration of the green box is going to equal to 1 meter per second squared. Now we know that acceleration is going to equal to the F net on that box divided by the mass of that box. So we know that the F net of the green box is equal to m of that box, which is 6 kg times its acceleration, which is 1 meters per second squared. So the F net on the green box is 6 newtons. And since the net force on the green box is just the contact force between the two boxes, we know that the contact force between the boxes is 6 newtons. And a quick side note before we move on, we can get the same answer of 6 newtons if we isolate this pink box over here. All we'd have to do is set the net force of the pink box equal to 10 minus the contact force, Fg on P, And then we can set that equal to the the mass of the box, which is 4 times the acceleration of the system. And you can see here that this will give you 6. It is just a longer way to do it because we're dealing with 2 forces, whereas for the green box, the net force is what we're trying to find. But you can always use this other way to check your work if you want. This would give you 6 newtons, so yeah. Okay, I've erased the ink on our slide, and now we're going to talk about this second part over here. If the same 10 newtons is applied to the box of larger mass, would the contact force be greater, less than, or the same? Okay, so the first note I want to make here is that the acceleration of the system between the two scenarios is going to be the same. And that's because the net force being applied to the system is the same, and so is the mass. It's just that the system is positioned differently. Now, keeping that in mind, we know that the contact force between the boxes is what pushes these rightmost box. In this top case, it's the green, and in the bottom case, it's the pink. We also know that the mass of the green box is greater than the mass of the pink box. If both boxes are expected to accelerate at that same rate, but the green box has a greater mass than the pink box, it obviously needs a greater force to be able to accelerate it at that rate than the pink box. Since this force is the contact force between the two boxes, we know that in the second scenario, this contact force is going to be weird glitching. The second scenario, the contact force between the boxes is going to be less than the first scenario. Another way to look at this problem is just by looking at the net force specifically on the green box. We know that the boxes in both scenarios have to accelerate at the same rate, so the net force specifically on the green box has to be equal between the two scenarios. In the first scenario, the net force on the box is just the contact force. In the second scenario, the net force on the green box is 10 newtons from the external force minus the contact force. Now these two values, the contact force in the scenario 1 and 10 minus the contact force in scenario 2, must be equal to each other. So from this, we can easily tell that the contact force in the first scenario must be greater than the second one. So that's just another way you could look at this problem. Okay, so now we're going to go over the application of tension force in third law. This is pretty similar to when we were talking about tension force in pulleys and other system of boxes. Okay, so we have this system of boxes that's being pulled to the right by an external force, which is this blue arrow over here. Now the idea is the tension force of the green box pulling on the pink and the pink box pulling on the green are equal. These are a third law force pair and internal to the system. Keeping this in mind, let's draw individual FBDs for each box. Starting with the green box, we can draw on its weight and normal force. Okay, so now the tension force over here that's being applied to the whole system is specifically being applied to the green box. So we're going to draw that on. And FT. Next, we have the tension force of the pink box on the green. Let's think about the size of this force for a moment. Would it be greater than, equal to, or less than the big tension force? It must be smaller in magnitude than the blue tension force. Why? Let's step back and look at the whole system for a second. The tension force acts on the whole system, making it go from being at rest to moving towards the right. So the whole system must accelerate to the right, and we know that the individual parts of a system accelerate at the same rate as a whole, so the green box must accelerate to the right, meaning its net force also points to the right. And for this to happen, this FT over here pointing to the right must be greater than the force of pink on green, pulling it to the left. Alright, so now let's draw the FBD for the pink box. This one's pretty simple. We don't draw this FT force on the pink box because although it acts as an external force on the system, it's not pulling specifically on the pink box. So what makes this box move? That's just the tension force of green on pink, which is the force pair of pink on green. So it's going to be the same magnitude as the FP on G. Let's call that FG on P. And this works out. The pink box's net force is pointing to the right, meaning it accelerates to the right as it should. So the key takeaway for this type of setup is that the tension in the string connecting the two boxes is not equal to the external tension force pulling the whole system. Instead, we can think of it like some of the external net force is dedicated to pulling the first box, and some of it is dedicated to pulling the second. It's a lot like the touching boxes we saw a moment ago. The external force that pushed the two boxes was not equal to the contact force between the two boxes. Okay, So now let's apply this knowledge and do an example problem. Example number 5. 3 connected boxes are pulled to the right by a tension force of magnitude 2,640 newtons. Assume no friction. What is the acceleration of the system? What is the tension force between the green and blue cars? And if the tension force were to pull the system to the left via the blue box instead, would this tension force increase or decrease in magnitude? Okay, so for the first part, we have to find the acceleration of the whole system. Think about how we might do that for a second. Well, this is just a second law problem. Ignoring internal forces, let's just take a look at the system as a whole. The only external force, and therefore the net force, is this 2,640 Newton tension force over here. We know the total mass of the system, which we can find by adding up the masses of the 3 boxes. So using the second equation, we can find the acceleration of the system. We have F net equals ma. F net is 2,640, and that's going to equal the masses of the 3 boxes added together, so 454 plus 905 plus 845 times A. And when you math this all out, you get 2,640 divided by 2,204, which gives you 1.20 meters per second squared. So there's our acceleration. Okay, so next we have to find the tension force between the blue and green cars. Here's where third law comes in. So the tension force between these cars, or in the string that's connecting them, is the force of blue on green and the force of green on blue, the third law force pair. Think about how might we find this force for a moment. Well, since this is a force internal to the system, we need to isolate either the blue or the green box to figure out the magnitude. This works because we have the masses and accelerations of each box. Remember, this 1.2 over here is going to be the acceleration of each box individually as well. And so we can use this information to find the net force on each individual box. So let's draw the FBDs of the green and blue boxes. The green over here, I'm going to draw the FG and FN, which I'm not labeling them. The green has a force of pink pulling it to the right, so F pink on green. And then it has the force of blue box pulling it to the left, so F blue on green. Okay, and this is the force that we're trying to solve for. Now with the blue box over here, same, we have gravity and normal force. And then the only force on this one is the pull of green on blue, Fg on blue. And this is the force we're trying to find. Remember, these 2 circled forces are going to be the same magnitude. So which box is easier to use to find the tension force between the green and the blue? That would be the blue box, because the net force on it is the force we want to find. The green box would be more of a hassle to use, because first we'd have to find F pink on green, which we don't even know, and then subtract F blue on green from that to find the net force. In other words, our setup would look like this. F blue on green equal to ma. We know these two, we'd have to find this using more calculations by isolating the pink box, and then we'd have to isolate this to solve. It's doable, it's just more of a hassle. With the blue box, our equation would look like this. Fg on B equals ma. This force that we're trying to find is already isolated, and we know these two already, so it's just easier. Okay, so we can solve. I'm going to do this down here because it's just, I need more space. So Fg on B is equal to ma, which we know that the mass of the blue box is 454 kg, and then its acceleration is 1.20 meters per second squared. So this gives us 545 newtons. Okay, so the tension force over here between the blue and green boxes is 545 newtons. Okay, I've erased most of the ink on our slide, and now we're going to talk about the last part. If the tension force that's acting on the whole system were to pull the blue box instead of the pink box, so it would look like this, the setup, then how would that affect the magnitude of tension force between the blue and green boxes? Would it increase, decrease, or stay the same? Okay, so what I'm going to do is I'm going to call our original setup the first scenario and this new setup our second scenario. And instead of using numbers, let's think about this conceptually first. In the first scenario, the tension between the boxes is caused by the green box pulling just the blue box. So I'm going to draw that out real quick. If this is the string that we're trying to find the tension in, just this blue box is being pulled. Now, in the second scenario, the tension between these boxes is caused by the blue box pulling both the green and the pink boxes. So again, if this is the string in which we want to find the tension, it's pulling the green box and the pink box. Now, we know that between the two scenarios, the acceleration of the system and the individual boxes won't change in magnitude. This is because the mass of the boxes, or the mass of the whole system, and the magnitude of the F net pulling the system don't change. So all that changes is the acceleration's direction, not its magnitude. So if the tension force between the green and blue boxes is responsible for pulling more mass in the second scenario, which is both the green and the pink boxes, than it is in the first scenario, which is just the blue box, but at the same acceleration, then this force in the string must be higher in the second scenario. And we can check this with math. Let's draw the FBD for the blue box and in the second scenario, so this one over here, and then we can actually solve for this FT. Okay, so here's the blue box's FBD. We got, oh my god, that's such a horrible box. We got weight and normal force over here. Okay, and then we're going to draw FT. And I'm going to label FT as negative because we're pulling it in the opposite direction now. Okay, and then on this side, we have the force of green on blue. So let's set up our second law equation. We know that the net force is that tension force plus the F green on blue. And then that's going to equal, whoops, hold on, let me erase this. That's going to equal the mass of this box, which is 454, times the acceleration of the system, which is negative 1.20. And again, I made the acceleration negative as well because our system's moving in the opposite direction now. It's accelerating in the opposite direction. Okay, so when we isolate Fg on blue, we get 2640 minus 544.8, and this gives us 2095 newtons. And as you can see, this tension force is way, way higher than the tension force in the original scenario, which was 545 newtons. But you don't have to do all this math to solve the problem. If you think about it conceptually, like we did with the two scenarios, then you can just solve it with words. Okay, so that was the end of the lesson part of the third law video. If you want to try your hand at some conceptual AP-style practice problems, be sure to check out part 2, which is linked in the description box. If you found this video helpful, please be sure to like, subscribe, or share, and see you guys next time. Bye!